Thank you. And my co-author on this work is Jiaqing Zhang from Caltech. All right, so I'm going to start out introducing the problem that really needs no introduction in this group, but I will introduce it anyway. So we're going to be looking at the local Hamiltonian problem, which captures local energy interactions in many-body systems, and these arise in quantum chemistry, condensed matter physics. So we have a Hermitian operator operating on an n-qubit or qubit system, sum of operators, each of which operates on a constant set of qubits. And we're interested in the ground state properties. So in condensed matter physics or chemistry, one might be interested in properties of the ground state. And Kitaev famously framed this problem as a decision problem so that we can study it through the lens of computational complexity. So in this version of the problem, you're given the Hamiltonian, which has a nice succinct description, and two thresholds with a 1/poly gap between them, and you're deciding between whether the ground energy is less than A or greater than B. And Kitaev also famously showed that this problem is complete for the class QMA. So this is the quantum version of NP. The verifier can produce a quantum witness as opposed to a classical one, and the verifier is a quantum polynomial time algorithm. And we strongly believe that quantum QMA is a strictly larger class than NP. In particular, we believe that QMA complete problems are strictly harder than their NP hard equivalents. So the local Hamiltonian problem can be seen as a quantum version of Boolean satisfiability, or more generally, constraint satisfaction. So it's natural to ask, what is it about the local Hamiltonian problem that makes it quantum? What are the properties that make it harder or more quantum in that sense? Or conversely, if we add some additional constraints or assume some additional properties, does that suddenly make the problem classical? And with this question in mind, we're going to be looking at commuting Hamiltonians, a special case where all of the terms pairwise commute with each other. Okay. So there are various reasons why one might study commuting local Hamiltonians. They are physically motivated. There are physical commuting Hamiltonians of interest. But from a computational point of view, the stabilizer formalism is the basis for most quantum error correcting codes, and stabilizer codes can be seen as the ground states of commuting local Hamiltonians, for one. And the commuting problem has been an interesting test ground for a lot of fundamental and very difficult questions that we encounter in computational quantum complexity. So for example, it's related to the quantum PCP conjecture. It's come up in understanding the area law and the area law connection to whether ground states have succinct classical descriptions. It comes up in the context of thermalization and computing Gibbs states. So it's an important test ground, and the complexity of this class of Hamiltonians is still largely unresolved. So we're asking, is commuting local Hamiltonian inside NP? And there are reasons to believe that the commuting local Hamiltonian problem has a classical nature to it. So for one thing, this intuition stems in part from the uncertainty principle, which says that it's the commuting nature of observables that makes quantum mechanics different than the classical world. Also, if you have a commuting Hamiltonian, then all of those terms can be simultaneously diagonalized on a single basis. So every eigenstate of the entire system can be labeled with a vector that indicates its eigenvalue for each individual term. And this classical description suggests that there might be some classical structure to these states. And indeed, there's been a lot of interesting work showing very special classes of a commuting local Hamiltonian are contained in NP. So most of this work does so in a very strong sense. Many results show that the ground state of special classes of commuting local Hamiltonians have trivial ground states, meaning that they can be constructed by constant depth circuits. So that implies that the entanglement in those states is entirely local. So Bobby and Viali were the first ones to introduce the commuting problem back in 2003. And despite about 2 decades of work, the complexity is largely unresolved. And what Bravi Viali did in their original paper is they introduced a mathematical framework based on C-star algebras, and this produced a structural lemma. And what the structural lemma says is when you have two commuting operators that operate on a common qubit, those operators sort of carve up the Hilbert space of that qubit in an interesting way. So it's a combination of direct sum and tensor product. And if you know where to look inside the Hilbert space of this common qubit that they share, and this is part of the classical hint that would be given by an NP prover, then a tensor product structure emerges and essentially disentangles the two operators. So this gives rise to sort of a localized structure. And they proved famously in their first paper that any two local commuting Hamiltonian is inside NP because the entanglement is highly localized. And then this was extended in later work by Aharonov and Eldar to show that this also extends to 3 local qubits and 3 local operators on qubits with a nearly Euclidean geometry. And all of this work makes extensive use of that structural lemma. Okay, and all of this, of course, shows that the ground state for this set of special classes is highly trivial. Now, of course, we know that this isn't always going to be the case for commuting local Hamiltonians because we have, as a famous example, the toric code. And we know that the toric code, the ground states are highly entangled and that there's no trivial ground state for the toric code. So in order to approach commuting Hamiltonians in full generality, we're going to need new techniques to do so. And there are 2 important predecessors to this work that study a class of commuting Hamiltonians that include the toric code as a special case. So these 2 works study 4 local commuting Hamiltonians on a 2D lattice where there are qubits on the vertices of the lattice. Okay? And initially, there's a result by Norbert Schuck who shows that the problem is in NP. But interestingly, his proof is non-constructive. So meaning that he doesn't actually give a recipe for constructing the ground state, but just merely gives mathematical evidence that the projector onto the ground space has strictly positive trace. So that's, and then later, Aharonov, Kenneth, and I'm blanking on the name, gave a constructive proof, proving essentially that the ground states of this class of Hamiltonians are essentially equivalent to the toric code with some special sort of boundary qubits involved. So still showing it's an NP, but this time a constructive proof. So we're interested in the QDIT case, expanding the case of known what we know about this problem to higher dimensional particles. And in particular, we're interested in constructive proofs where we understand something about the structure of the ground state, or we can actually compute or construct these ground states. Bravi Viali also consider another special case, which is in their original paper, which is sort of a lesser known result. They consider factorized Hamiltonians where each term is a product of individual operators on each individual qubit. So, and I'll say a little bit more about their result when I sort of compare it to what we did in our paper. Okay, so here's our setting. So we have a 2D grid. QDITs sit on the vertices, and our terms are plaquettes. So the plaquette P operates non-trivially on the 4 particles on the corner of the plaquettes. Now, oftentimes you see the toric code with the qubits on the edges, and you have star terms and plaquette terms. This is sort of an equivalent formulation. If it were to be the toric code, it would be a checkerboard pattern with the black squares being X's and the red squares being Z's. Okay, and the local Hamiltonian, of course, is the sum of all of these plaquette terms. So we're interested in the same question. We're interested in the ground energy. Now, one thing that we can do that simplifies the problem a little bit is that we can assume that each Hamiltonian term is a projector. For the purposes of showing that the problem's in NP, we can reduce it to a simpler case where the individual terms are projectors, and we're looking for a frustration-free ground state. So we're looking for a ground state with 0 energy that simultaneously satisfies all the terms. This reduction works, but it doesn't work in the factorized case, because when you do this projection, you no longer preserve the factorized structure. Okay, so our first result is that we extend the case of qubit Hamiltonians to Q-trits. So we're going up 1 dimension in the particles. And the case of Q-trits is considerably tricky, and it adds a considerable difficulty to the problem. And intuitively, if you apply the structural lemma, you can think of 2 operators that share, say, a qubit between them. You can apply the structural lemma, and it carves up the space of that qubit. Now, there are only so many ways that you can carve up a 2-dimensional space, and that's leveraged heavily in many of these results. So when we go to Q-trits, there's more complexity in terms of how that structural lemma plays out in terms of carving out the 3-dimensional space. And in particular, to illustrate sort of the difficulty in going to now to 1 additional dimension is in the qubit case, commutativity sort of acts transitively. So in other words, if I have an operator A operating on a qubit and it's not the identity, then it has unique eigenstates. If A commutes with B and A also commutes simultaneously with C, and they're all operating on a qubit, then we know that B and C mutually commute. This doesn't hold in the Q-trit case. So this sort of illustrates that the problem is considerably more complex. Okay, so when I talk about our key lemma and what we do to prove this, the key lemma actually works for higher dimensional particles, but we can't leverage it unless we're actually looking at Q-trits on 2D. So, okay, so that's the first theorem. And the second theorem is we look at factorized commuting local Hamiltonian, and we show that in the 2D setting, this is an NP. And furthermore, we give a complete characterization of the ground space of this set. So it's highly constructive in that sense. We show that it's essentially equal to a direct sum of stabilizer Hamiltonian. So you can take your entire Hilbert space, and there's a direct sum structure on that Hilbert space. And if you project onto each subspace given in that direct sum, you essentially get a stabilizer Hamiltonian. And we know what those look like. Now, to illustrate why this situation can be a little bit tricky, there are actually 2 ways that two factorized terms can commute with each other. In the first way, which we call the regular way, this is the terminology from the Bravi-Viali paper, the product of the 2 terms is non-zero. And if they're factorized and their product is non-zero and they commute, then each individual term, each individual factor on the qubits has to either commute or anti-commute. And so this gives rise to a stabilizer-like structure. Now, there's a second way that 2 factorized terms can commute, and that's if their product is 0. So if you look at this little example here, I have H1, which is this operator on the first qubit and some operator on the rest of the qubits. H2, which is another operator on the qubit 1 and some other B on the rest of the system. And the product of these 2 terms is 0. Now A and B can have any relationship to each other. They don't need to commute or anti-commute, and they can look very, very different from stabilizer Hamiltonians. So this suggests that it's possible to have ground states of these systems which have completely different topological order than stabilizer codes. And we showed that's actually not the case in 2D. So if you embed your Hamiltonian in a 2D structure that limits the connectivity enough that you can sort of eliminate the second possibility. So by carving up the Hilbert space into this direct sum decomposition and projecting onto each different subspace, you basically get rid of the second way of commuting, and you're left with pairs of operators that commute in this regular way. All right, so in the remaining time, so just to compare our results with Bravi-Viali, their result holds for any geometry. We're embedded in 2D. But we can handle larger dimensional particles, and our proof is entirely constructive. And there's an easier proof that's non-constructive by combining various techniques, but we go through the additional difficulty in order to get the complete characterization of the ground space. All right, so in the remaining time, what I'm going to do is walk you through sort of the key lemma that we use for theorem 1, which is the Q-trit case. And first, so we're going to assume now that all our terms are projectors, and we're just looking for a frustration-free ground state. So let's look at a simple example, and suppose that there's a Q-trit in your system, or Q-dit for that matter, such that the Hilbert space for that particle, there's a non-trivial decomposition, and all of the operators respect that decomposition. So if I were to write out all of these operators, they would be block diagonal in that decomposition. Well, this would be a great situation because I could make progress in my problem and do a self-reduction. All I'd need to know is if the original instance has a frustration-free ground state, then I know that there's a frustration-free ground state that lies entirely within one of these subspaces. So the prover just needs to whisper in my ear and tell me where it is, and then I can easily project down. Now, this isn't enough because if you can eliminate all of these, what we call them, if you can eliminate all these separable qubits, you've reduced the dimension of your problem, but you could exhaust this and still have a very complex Hamiltonian. So we introduced the notion of semi-separable qubits, which only requires that 3 of the operators respect this decomposition. And the 4th one can be kind of a wild card. So what do we do if we want to project down into one of these spaces? For operators terms P1, P2, and P3, it's clear we can just project. But before we can't do that. So what we do is we use a brute force method and we just apply the projector. Now this term is no longer a projector, and it's not clear that we have a commuting instance. We make it into a projector by rounding the eigenvalues. So any eigenvalue that's less than 0, we just round it down to 0, making it a projector. And then we actually prove that the resulting instance is commuting. Moreover, this is an actual valid self-reduction. So if there's a frustration-free ground state in the original problem, there's a way to project down to one of these subspaces and do this operation to get a new instance, and the new instance will have also a frustration-free ground state. So that's the key lemma. It's non-constructive because the frustration-free ground state in your new instance doesn't necessarily bear any resemblance to the ground state in the old one. Okay, but here it is stated. So, and this lemma works for any qubit and any geometry. And if you eliminate these semi-separable qubits, you get enough structure on your Hamiltonian that you can start to apply classical techniques. In particular, if I look at terms that overlap in a non-trivial way, I get chains of terms that can be managed with matrix product state techniques. All right, so let me just mention a few open problems. So our result for Q-trits is non-constructive. So one question is, can we make it constructive? It's not clear that the ground states have this nice stabilizer structure as it does in the qubit case. So that might be considerably more complex to do. And another question is, can we apply this lemma, which really does apply to larger dimensional particles, to other situations? And one candidate might be this 3 local Q-trit case, which has which would extend the known result. So we know that 3 local qubits is in NP, but can we extend it to Q-trits? More generally, we really don't know the complexity for larger dimensional particles. So is commuting a local Hamiltonian in 2D in NP for any arbitrary dimension particle? This is unknown. And is there evidence of hardness too? So I'm not necessarily sold that the general problem is inside NP. There's reason to believe that there's actual QMA hardness there. So the the jury's still out on the more general problem. So various open problems to work on. So thank you.
A great talk. We've got some time now for questions. If you'd like to ask a question, please come up to one of the microphones in the middle. And yeah, queue up to ask your question.
Thanks for the great talk. You mentioned in the end that that there might be some evidence that commuting local Hamiltonian is QMA hard.
Well, depends on what you think of as evidence. So this isn't the local Hamiltonian problem, but the ground state connectivity problem, for example, is QCMA hard, and that's true for the commuting case and the non-commuting case. My gut feeling is that for 2D, it probably sits inside NP. We just don't have sophisticated enough techniques, but I'm less sure about the general case where you have arbitrary interactions.
Yeah, I would see it more maybe like in QMA1 because of the property that like you sort of know that it will be a ground state of every
right. Yeah.
Every local term.
At least quantum in some sense, or not in it, not lying inside NP. So
thanks.
I don't know.
I've got a question. Could you give any intuition for what it is that breaks in the QDIC case that works in the QTRIC case when you go from the key lemma to the
sure. So the thing about 2 and 3 is that they're prime numbers. And so if you imagine a tensor product decomposition of a 2-dimensional space or a 3-dimensional space, one of those is going to be a trivial Hilbert space. So now when you go up to 4-dimensional particles, you can have a tensor product decomposition of that space that's 2 and 2. So you can imagine diagonal terms that decompose the space in one way, 2 and 2, and then on the other side, 2 and 2 in the other way. And those could be highly incompatible decompositions of the space. And if that happens on every particle, we have no idea what to do with that. So we thought when we went from 2 to 3, we'd have it for everything, but we were missing this subtlety. So.
Just to follow up on that. So can you say anything about more general prime dimension units?
Interesting. So like 5 dimensions or something like that. So there's still a few more complexities. So it's not simply the prime thing. That the 2 and 2 seems to be definitely a deal breaker for our current set of techniques. But we have a sort of a characterization of the induced algebras on these particles. So, in terms of how they decompose the space, whether it's 1, 1, and 1 or 1 and 2. And that still gets more complex in, say, the 5-dimensional case. But you do avoid this tensor product structure. So, but that might be the next thing to work on. So any prime dimensional particle would be certainly easier to tackle, I think, than the 4 case. Yeah.
Thank you.
Cool. If there's no more questions,
Thanks.
I want to thank Sandy again. And the next talk will begin in 5 minutes.